Alrighty, time for a smoking video on series. We're doing problem number 27, and the instruction is find the values of p for which the series is convergent. So, this is like a whole lot of problems in one. So you can see that the series is summing from n equals 2 to infinity of the terms -1 to the n divided by natural log of n to the p. So, this is an alternating series. Went ahead and wrote the problem down here. Alternating series. That probably means that I'm going to use the alternating series test. Helps that it's an 8.5 in alternating series. So remember, alternating series, what you want is you want the -1s to alternate, and then you want your terms, your an terms, that are always positive. And you can see that 1 over natural log of n to the p is going to be positive, right? So these are my an's. Now I have to establish two things for this test to hold. The first thing is that the limit as n goes to infinity of the an's goes to 0. So let's see, 1 over natural log of n to the p. Okay, so what power? Now I happen to know that natural log of n as n goes to infinity, that goes to infinity. So what power could I raise that to? What power could I raise this thing to so that this whole thing would go to 0? Well, as long as this somehow stays in the denominator, all is well. So if I took the square root, if I took to the 1/2 power, that would work great. What if I took to the second power? Well, if this is going to infinity and this is squared, it's going to infinity even faster. So this will equal 0 as long as p is greater than 0. Now if p happened to be 0, this is going to infinity, but you have to the 0th power. Well, that's 1. That's kind of useless. That does not go to 0, right? That would go to 1. So it would go to 1 if p was equal to 0. What if p was less than 0? Okay, that would actually flip it to the numerator, and that would mean that the whole thing would diverge to infinity. So this is that case we care about. That's the case that we have some hope of this thing actually being productive, of going the direction that we want it to. Now the other thing that we need let's see, an plus 1 less than or equal to an. Now we can do that two ways. We can either just sort of inspect the terms, or I could take the derivative of this thing. I could take the derivative of my an's and make sure that the derivative is negative. In other words, the slope is decreasing. So let's just try inspecting the terms. So 1 over natural log of n to the, sorry, this would be n plus 1, I guess. N plus 1 to the p. Is that, I'll put a question mark there to indicate I don't know whether it's true, is that less than or equal to the natural log of n plus 1 to the, sorry, this is just natural log of n to the p. So, what if I cross multiplied, so this would be the same as saying the natural log of n to the p is less than or equal to natural log of n plus 1 to the p. Now, as long as p is, let's see, if p is not equal to 0, I guess I could multiply by the reciprocal of p. So, if p were like the 7th, I could raise it to the 1/7 power. I could take the 7th root, and even if p were the 1/7, that would work fine, and I would get out. And remember, the only case that's even a candidate here is p greater than 0. So as long as p is greater than 0, we will take the root, and that's the same as saying natural log of n is less than or equal to natural log of n plus 1, which frankly you could cancel the natural logarithms on both sides, and that's pretty clearly true. So that's true. That's true. As long as p is greater than 0. So the series converges for all p greater than 0 by the alternating series test.